A rectangle steel bar, 37.5 wide and 50 millimeter thick, is pinned at each end and subject to axial compression. The bar has a length of 1.75. The modulus of elasticity is 200 gigapascal. What is the critical buckling load? Anyway, how do you solve this is a question. You might think, first of all, I need to think of where it's going to bend because another thing you need to know is which of these is the base. If I give you 37.5 and 50 millimeters, which way you're going to think you're going to bend? The way you're going to bend is this way. And you can test this out by a toothpick or a piece of paper. If you put down over here like a slim piece of paper, the where you're going to bend is the long side, like one piece of paper. Like let me turn on my camera for once to show you what I mean by that. Um, because I think this is a very important intuitive lesson. So you get this, right? If I were to push down, where does it buckle? It buckles on the long side. It never buckles like this. You can't have that. Always buckle on the long side. Why is this important? Well, in reality, sooner or later, you're going to have something like this right now, where it's uncertain where you're going to bend. And why does that matter? Well, because of your I over here, BH cubed divided by 12. Which one is the base? Which one is the change? So it's the 50 is the base in this case, and 37.5 cube is the change, and it's divided by 12. So in that case, here's what we're going to do. We're going to bring out the equation of power for buckling, which is this thing, critical buckling. PCR equal pi squared. Do not forget about the square. EI divided by KL square. Now, first thing is pin to pin, as they said over here. And here it says pinned at each end is subject to axial compression. So pin to pin is saying that this can be turned into pi square EI divided by L square. L is 1.75, by the way. Okay? So pi square parentheses 200 times 10 to the 9. And then your I, which should be equal to um, 50 multiplied by 37.5. And then it's cubed divided by 12. So grab your calculator. You know what to do. Grab your calculator and start plugging. You might be saying, well, there's something called units that you have to care about. And this is not the right units. And I can concur it's not. Therefore, you have to actually divide this by 4. So multiply whatever you got and 1 divided by 1000 by the power of 4 gets you the right answer. So I get like 0.12345. I get 7 of these, I think. And then 2, 2. That is a powerful tool right there. Um, anyways, with that said, you plug in that I and you have L, which is 1.75 squared. Do not forget about the square. And you plug into your calculator basically. Pi square, let's go for the division. Pi square multiplied by 200 multiplied by 10 square root of 9 multiplied by whatever came before. And then it's parentheses 1.75 parentheses square. And I get equal to 141800, which I'm assuming is the right answer, which is D. And that's the first question of this buckling section or column section, whatever this is called. And first question done. So determine the maximum resultant normal stress of A for the cantilever beam shown. I don't see this cantilever beam. I'm going to have to grab it in the original question. Give me. So here is determine the maximum normal stress at A for a cantilever beam shown. And there's no mass, no nothing. So here's the thing about cantilever. So normal stress, it says. So it's going to be P over A. And there's a plus or minus my equation over here. And this can be activated because this is shown. If this wasn't shown, it cannot be activated. Okay? Now you might be asking, yeah, clearly, but most of the time we wouldn't think that. How do you differentiate from this kind of question to another? Well, a lot of times they don't show the result, maximum, the word maximum, often, and also the fact that there's a diagram. Yeah. So clearly we can do now what we wanted to do, which is get P. And we need to do the sum of all forces ulterior equals 0, so we can do this to it. Now you can imagine what I'm about to do. AX is positive, and we know that's a decision I made for now, and it's going to be plus 225 cosine 45. Obviously, the direction is wrong, but it's AX equal whatever this is, which grab your calculator, and you can get cosine 45, parentheses. About 159 is kind of where I got. So 159.0990258 is our newtons. So that's the x direction. Now, we don't need a shear. We need what we call the moment now. So we can do a summation of moments, and we can do a summation of moments on A equal 0. Now, this one creates a moment here, actually. So basically, because it's fixed, it can create a moment here to balance everything out. And this moment is going to be called M. Most likely the reason why this happens. So we're going to do 350, wait, where's there? The moment over here, we're going to do M at A, and we're going to choose a negative direction for it for now. And this was -2. Yep. But we could change it to positive or whatever, depending on how you want to do it. And it's plus or minus, so we just have to figure out the max so far. So then we have to do this one, which is going to be another minus 350 newtons multiplied by 7. And then it's going to be plus 225 cosine theta, right? Equals 225. And then it's going to be multiplied by 5. And it's going to be minus 225 sine theta, which is 45 degrees. And then this one is also 7 equals 0. So M equals this result over here. So we can get our calculator out on it and then grab this already. Yep. I get -2768.198052 as our moment. With that moment in hand, obviously for some reason I have chosen the wrong direction on all of them, so that's fun. But that really shouldn't matter too much because now we can plug into here, which can tell you that minus 159 divided by area, which is 7.5 multiplied by 175, 1 over 100 meters square. That's true, but we can do that later. Plus the moment, which is going to actually be for us minus because we want the max resultant. And to get the max resultant, you have to do this. And then the C would be just 7.5, so 17.5 divided by 2. But we can check on that later for now. We don't have to do it right now. And then we can divide this by I, which is also going to be I equal B over H cubed divided by 12, which we can see is tall 1. So this basically implies that, yes, it will work. And if you're asking why the long side when I said that about that quote, because we have a direction that's 2D, and it's going to be a cut of it, as you can see. And that's why this is happening. So if you want, you can get rid of the absolute value later on, but for now, we just plug into our calculator and see what we get. And if you want a little bit cleaner, like of what's happening. What's C? 17.5 divided by 2, divided by 7.5, 17.5 cubed divided by 12. Okay. And then there's obviously a factor here that's going to be about getting the right ratio, which I'll just do in my calculator. So if you plug in all the numbers, you get 7242808, which is basically A if you round up, and if you delete the 4 over here, 4 digits over here because it's kilonewtons, kilopascals, sorry. So this is pascals, kilopascals is 7.242 kilopascals, which is about A. Right. Okay, here we have to figure out the most plastic deformation that could be happening. So plastic deformation is a little different. It's not beam deflection. It's when the column is being deflected. So you can imagine that it's actually a cantilever rod shown for tension and compression. We kind of both know what this is, mostly because we know which part of the question we're looking for, but we first have to get a moment of this question. And might be asking, why not use the S equation to get deflection and all that? Because it's plastic deformation. What does plastic deformation mean? You'll see soon. Basically now you have to do a moment on 0 over here at the centroid, so it's over here. And then with that said, you have to do what we call, okay, 75, right? And then it's going to be divided by 2 minus 25. Grab your calculator and put that in here. So 75 divided by 2 minus 25 equal about 12.5 millimeters. That's going to be one of the rotation vectors. With that said, we can do what we call close to this one. So F sine 30 multiplied by some length distance, f cosine 30, and we know the length distance for this one, 12.5 millimeters, which we'll have to divide by 1,000 because of that. And then there's this is going to be minus, both of them are minus, so there's going to be a plus m over here equals 0 as a reaction force, and the reaction force is always negative, so, well, everything's negative here. Wow, yeah. So the direction of the moment is wrong. It's going to be the opposite way, which is interesting. Not really that bad because the f-axis is plus or minus, so we just can change it to minus and so forth. So over here is 3. So with that said, we have all the equations. So we can just do f minus parentheses sine 30 parentheses 3 minus plus now cosine 30 12.5 divided by 1,000. And move the other side. So plus and then minus again. So m equals this. So m equals f times whatever this is, which is sine 30 parentheses multiplied by 30 plus division cosine 30 multiplied by 12.5 divided by 1,000. I get 1.51082 F. So the moment over here equals that, so keep that moment alive. All right. And now we do have to do summation of force initially. Yeah, we do because actually we don't have to. We can just apply this notation from here. P over A plus or minus MC divided by Y. We know these equations to heart. And P over A, P is basically F cosine 30 divided by area, which is a rod, so it's pi parentheses 75 divided by 2 square, so that's 1 divided by 1,000 square. Plus or minus, we're just going to not do the negative to make this a 1.5108 F, and then C will be about 75 divided by 2 thousand because of the millimeters, right? Okay. Next up will be the y. No, not the y. My apologies. It will be the I in this equation. I equal pi a to the 4 power over 4 for this one. Yep. So you can imagine it's pi divided by 4 parentheses, whatever 75 divided by 2,000 looks like. And then it's the 4th power. We do the first, and then we have f, and then this equals that. Yes. Now, this over here is this basically. So you can imagine that to prevent plastic deformation, the max over there, that's omega max basically. So there's no safety factor, so we use that instead. Another notation that you have to know, 276 megapascals over here, equal F parentheses cosine 30 and blah, 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 blah. So I'm gonna do simplify this version and then this first, and then we can move from there. So divide cosine 30, bottom, parentheses divide 75 divided by 2, 2,000. Let's just make it simpler for us. Parentheses square equals about 196 F 1.5108 multiplied by 75 divided by 2,000 pi divided by 4 multiply parentheses divide 75 divided by 2,000 parentheses to the 4th power. Okay. Hopefully I didn't make a mistake on anything of this. So this plus this. And then moment of truth, if there is a mistake, then it'll show up when I multiply by 6, the power 6 to oh, it already showed up because it can't be that big. But let's just keep on going. I think it might be the right answer. So we were going to add these together and we get 36673 F. So if I do 276 divided by 36673. Oh, I get an answer, so it must be correct. I thought it would be too big. My intuition was wrong this time. So 727525, that is Newton, so you get D. Yeah, sometimes my intuition is wrong. So make sure to do the math instead of relying on intuition. Intuition is half times wrong, so it's the math that you need to get to make sure you're not going into a wrong direction. What's the maximum elastic deformation of the rod at the point A due to the concentration force of F? So F is over here. This is the deflection in the over here. Let's just go over here. There is two things over here that I need to actually care about. It's the same thing we always cared about. If you go down here, there is a point force at L, and there is a moment force at L. Both of them are applied to over here. You can imagine the moment force being quite substantial here because it's you know. So here's the thing. This is a local moment force on to this plane over here. So be careful about that. It's not the moment on this end fix. So with that said, let's grab those equations real quick. The first thing I need to grab is this one, the delta 1 equals negative p over a squared, which I'm just going to say it. I'm just going to make the adjustment because we all know, I did it like three times already, that this turns into this. And delta 2 is this one, which is mol squared divided by 2ei. We all know that's the one that we're using. So it's delta 1 plus delta 2. Do I know how it's going to play out? We'll see. Squared divided by 2ei. So with that said, we have a deflection we can get, and finally we can get delta t total. So delta t equal negative. What was the force again over here? It was d I chose, so 7,530 newtons. So we can imagine this p being 7,530. It's going to be sine of 30. I'm going to do it one at a time like I usually do. I don't like how I realize doing it separately is always better. I don't like anyone doing it like in one way. One way. It's actually pretty bad to do it that way. 3 multiplied by e, which is 69 times 10 to the 9. And now let's get myself I. I is pi a4 divided by 2. Divided by 4, sorry. J is divided by 2. At this point, I think is a you need to memorize it. I don't want to say it, but in reality, these equations, it looks like some of them are just need to be memorized. And this bottom one, bingo bingo, you need to memorize it because at this point, I've been using that so much that I have to just memorize it at this point. So that is scary actually that you have to memorize that actually. Um, because the amount of times I've used it is too much. Oh, by the way, this is going downwards, so the deflection is this way. Now you can make it negative, but if you choose this direction as positive, it doesn't matter. But if you choose the other way, yeah, go ahead. You can make this negative. But then you have to think about the moment and which direction it goes up to, because the moment you can check over here, this way is going upwards, which is for me negative sometimes. Okay, I'm gonna keep it real with you and just keep it this way, negative, because that's probably the way you're thinking in your brain. So here is the final, kind of the first one over here. This first one gives you like negative 0.316. And over here, we're about to do the second one over here, which I don't really know what it's going to give me, but to just plug in the numbers and you should get something. Yep. And they're both negative because of the direction of the moment. Also, if you look at the beam bar, it'll actually go in the negative direction, just so you know. I will mention that you could have just added it positively and gotten the same answer. So, I mean, it's your choice on how you achieve your goals there. But either way, you have a beautiful answer there. Anyways, after you plug in your digits to your calculator, you can get an answer here. Take a while to get the answer. Okay, about 2,000. Let's just say to the fourth power. I get like 0.00342228. So we know it's D. I mean, we know it's D now because it's that thing is way too small for you to even consider anything. So it is basically, I mean, it's gonna be 0.319, which is 20. But in reality, you didn't have to even do that. The truth is because this is gonna be a negative and negative, they're gonna be adding each other, and you already got like something like like some high number. So this is just gonna add to it. So either way, you would have gotten the knowledge that it would be D. All right, a real rectangle steel bar supports a concentrated load of 58.5 kilonewtons. Both ends are fixed, built in. If the modulus of electricity is 210 gigapascals, so what is the maximum length of the bar that can without experience buckling? Here's the trick over here. I will also mention that the long side is where the IB where the bend happens. Like this, it will bend like this, basically. It'll bend like this, as we discussed previously in the first like lesson I gave you about this. So this is a buckling thing. This is a buckling. Remember, buckling is different than what you think. So over here, does it give it the maximum stress or what is it? It gives me P critical instead. Okay, that's fair. All right, we have to start by looking over here with the force over here. PR equal pi square EI over KL. We know that this is squared, by the way. Do not forget the square. That's really important for you guys to understand because I make that mistake all the time. L square pi EI, basically. And with that being said, now we can figure out everything else over here. The bend moment I already split. We start from here, basically. We have the equations over here. We know that PCR is equal to this number over here. So with that said, we can just see what the length is for it to be critical, and we're done. So for that take, first of all, 0.5 L squared parentheses equal pi over square 210 times 10 to the 9 of I. Why I'm keeping I like that is I is literally a pain in the ass to calculate every time you do it because of how much it's in millimeters and you have to change it to like meters and continuously change it back. It's a pain in the ass to calculate, I'll be honest. And then you do square root of this, and L equals 1 divided by 0.5 square root of pi square 210 multiplied by 10 to the 9. And I, the most annoying thing to ever calculate, 500. And then with that, you should get the answer. But also, this is plus or minus, so it's interesting. But it should not be anything bad. So it's 1 over 0.5 second square root of division pi square multiplied by 2 tenths multiplied by 10 square root of 4. Yeah, and also you just have to double check and do this one. There's a bunch of squares in here, and it's very easy for you to like not write the right square. And that was in square to the power to 9. My apologies. I think I said something wrong. It is a steel bar, so you can imagine what the base is. The base is 20. Yeah, so yeah. Um, no, not base is not 20. Oh, god damn, it's not 20. So it's bending this way. So again, what a tricky bastard that this is. The base is actually 30 by 20 cube divided by 12 because for a bend, it's the longer side that's the base. I don't like how the question set it up. Again, they should be more mindful, in my opinion, of how they showcase the thing, but they won't do that because we're engineers and you're supposed to be able to do whatever calculation is given by just looking at something. Uh, Anyways, I don't know what I just said. Um, I was saying gibberish, and I hope it sounded something smart. Oh my God, it's taking like 5 minutes to input something in my calculator. Okay, okay. So let me input it. So with this, I get about 1.68 or 1.7. So it's B. Yeah, this one's B. And you might be asking, I mean, yeah, that's definitely B. Yeah, and yep. Fun fact, um, nah, I'm not gonna say it. That's how you solve it. So make sure to do that. And yeah, we can now move on. A pin-connected tripod frame consists of three round steel bars A, B, A, C, and AD as shown. Each bar is 75 centimeters long and has a cross-section area of 3 centimeters square. Okay. Okay. So these pin tripod frames. All right, they're rods basically. Each bar has 75 centimeter cross-section area, and the cross-section area is 3 centimeters squared. So we're gonna go centimeters. Each bar is 75 long. Okay, fair enough. The Young's modulus is of steel is 210 gigapascals. A vertical of 9,000 load is supported at the common point A. If the column buckling based Euler's formula is only condition, what is the maximum force allowed? Euler's formula, Euler's. Oh, that's gonna be using one of these again, right? Here it is. Euler's formula, which is PCR equal pi square EI divided by KL parentheses square. And with that said, we have to get what is the approximate maximum force of each rod. Okay. So, hmm, interesting. All right. It's a tripod? So this is like a 3D question. Really whack, I must admit. Hmm, very whack indeed. Obviously, it's asking for PC. Or so the only condition is this. So this is like I don't like this question. This is obviously a bad question. Yeah, this is pretty much a horrible question. Honestly. Let me think about it for a second. Oh yeah. I'm just gonna say this question is awful. I finally got it working. Um, so the key part over here is this portion over here that says that only this thing is important, which means that you basically just plug and chug it over here. So this one I didn't understand at all, but basically none of this matters. I'm going to say this question is absolute bullshit because the entire side view and end view is completely useless. It actually just hurts you. And the basically, you can ignore everything. You can ignore the 9,000. This question is horrible. This question is beyond the worst question I've ever seen in my life. Whoever made this, prison for you. Uh, this is just bullshit. I've never seen more bullshit of a bullshit question before. And if the FA exam gets this question, I'm purposely not going to do this one. Yeah, I get the answer. But yeah, I don't want to ever see this question ever again. Um, yeah, yeah, and but the show must go on. I must still showcase this question. So the answer is about D. But yeah, I'm not even going to do this properly. I didn't in my calculator. I got two something, and I got 233 something, and that's about 220,000. I rounded up like crazy, just because I feel like this question is bullshit. I've never seen more bullshit in my life. This question is awful, and has no place to be here. Honestly, I don't know what the point of this question was, and whoever cooked up that was a crime right there. A square steel column with a solid cross-section is pinned at both sides at its base and top. The column is 5 meters in height and supported by a load of 3.5 meganewtons. The modulus of electricity is 210 gigapascals. It must be something like steel. That must be because I keep on seeing that 210 gigapascals. I'll double check that later, but most likely it is. Anyways, with that said, what's the minimum cross section of to avoid buckling? We all know what to do. It's fixed, right? So that means we can apply this powerful equations we have, which is pi r e I over k l square, parentheses square. Remember those two, this is squared by this. Anyways, with that said, we're given this portion, we're given this portion, we're given this portion because k equals 1 for that. So basically, the only thing we don't have is I, which we're going to solve. We need that to get the cross-sectional B or H. So first of all, let's simplify this thing a little bit. Divided by E pi square, and that equals I. And we know what I equals really, because we have done it multiple times for a squared thing, which is equal to saying BH cubed divided by 12, but it's actually B to the fourth divided by 12 in this case. So 12 parentheses PCR parentheses K L parentheses square divided by E pi parentheses by the fourth power equals B. With that play in mind, we can get the any of these things over here. Really just plug into your calculator. So you do second, you do 4 first of all, and then you do that. You could have done 1 over 4 and then make it exponent 2. Both ways work. Either way, you get the answer. So it is 3.5 multiplied by 10 by the square root of 6. Okay. And then it's multiplied by whatever the length is. The length L is looks like it's 5. So 5 squared divided by E, which is 210 multiplied by 10 square root of 9. And then I forgot the pi square. Don't forget about the pi square. It's the one part that is so easy to mistake because you don't think pi square is actually pretty abnormal. Like you don't usually use that. So I get 0.150 meters. Remember it's cm, so you divide. So it's multiplied by 100. So it's C. The answer to this question is C. And yeah, let's get the answer in here and move on to the next section. So a steel column with a cross section of 12 by 16 is 4 meters in height and fixed at its base. Fixed is, I believe, 0.5. The column, yeah, it's 0.5, I believe. So different rules, but actually fixed, right? 0.5, right? Fixed. No, fixed is 0.5. Oh, six fixed only at the base. The column is pinned at the top. So K is equal to 0.7. So always read a little bit. A steel column with a cross section of 12 by 16 is 4 meters in length, height, and the fixed at its base, the column is pinned at the top, so that already gives me that k equals 0.4, 7, sorry, 0.7. And if you don't remember that, the best thing you can do if you don't remember that, and you shouldn't remember this, you should just go over here and realize 0.7. Oh yeah. I only know it because I did this question multiple times before. Anyways, um, anyways, with that being said, we can move to what's the question asking. The column modulus of electricity is 2, 1 times 10 to the 3? Really? That sounds pretty tiny to me. Um, well, you guys can double check that one. I'm not convinced that that is actually uh the 3. Yeah, actually, it might be a 5. I can barely read that, man. Okay. All right. And the height, so this E, the height equals 4 meters, and then we have the cross-sectional area, and basically, we have what do we have? We have the stress. No, we have what are we looking for? We're looking for the maximum theoretical vertical load. Okay, so the CR equal this. So this is basically using this equation. And it might look like an easy equation to use, honestly. But honestly, it's not because of people get tricked by it very easily, in my opinion. Especially when you use a calculator that is pretty small. You see, hand calculators, you can't see everything really clearly. So in my opinion, it makes it harder. In my opinion, if the testing company allowed a better calculator, this test would be way more appealing to me. But like not a graphing calculator, but I guess there's not really a good calculator above board. Now you might be asking, which one's B, which one is H? But at this point, you should realize something. When you're bending like this. The long side is being bent. The long side is the base. So it should be 16 and then 12 cube divided by 12. Okay? If you still don't get that, then grab a piece of paper and do what I'm gonna do with do what I'm gonna do. I'm gonna get my camera out. Gonna show you a book. So push this. It's gonna buckle this way. This way. When you push, it's gonna buckle this way or this way, and you see that it's never gonna buckle this way. It's not. It's not gonna happen often. This is one of the best books in the world. It's Elements of Gas Dynamics. Beautiful book. If you want to read it, I recommend it heavily. Another book I recommend is this Fluid Books. Um, I can't find it. Somewhere in there. I have a huge I actually need to find it because that's one of the best books ever, and it's by Action. Oh, oh, where is it? It's a question now. I actually want to find it now. Um, yeah, let me just go find it first. I can't seem to find it. The Action book, very great book if you ever have it. I'm sure it's here, unless I threw it away by accident, which I doubt. Unlikely. Anyways, oh, found it. Oh, me, me a long time. Found it. Okay. So this over here is a great book, in my opinion. Once I grab it from my library or fake library. Here it is. This book is really good. Anyway, same test. Like if you do it like this, it bends this way. That's buckling. So you see how it never bends this way? The other way, like if you're trying to like bend it, like this doesn't bend, like this doesn't compress that way. Anyways, great read. Anyways, before, yeah. Anyway, let's continue with this. That was a side tangent of epic proportion. Uh, what a silly man I am to show that off. Okay, so pi square multiplied by 2.1 times 10 to the square root of 5 multiplied by division 16 multiplied by 12 cubic divided by 12. And then because these are in cm, so if you don't know, cm is 100 cm equals 1 meter, if I was remember correctly. And to get 1 meter to lead that, you have to divide by 100. So is 1 divided by 100 to the power of a 4 because it's 4. And then the bottom over here is 0 point parentheses 4 multiplied by 4 parentheses by square. And I get something is right. With that, I said I get 6.09. Uh, I think, well, that's what I get. Oh, I didn't do times by 10 to the 6 over here. So it is mega. This one's supposed to be 10 to the 6 also again. So this is 6 mega, so C. Yeah, it took a little while, but got the answer. Next one over here, a steel column with a cross section of 12 by 16 is 4 centimeter. Didn't we just do this? Oh wow. Okay. I think this is like a repeat question maybe. Um, Let me check up here. 2.1. This question is pretty looks the same as before, but it's not. Why is it not, you may ask? Because you have to look at this thing. You have to look at it as a 3D object. In a 3D object, it looks like this, right? And the braces are okay. The column is braced against the buckling of the weak direction. So that means in the weak direction is pinned. So moving this way is like this, like this. That part has been braced with a pin. Okay? But the column is braced against that and pin. Okay? So basically it's not allowing this to basically happen one way or another. How they pinned it? Well, if I had to guess, it probably was stopping this type of movement. So it might have been something like that. Okay? To stop the buckling. Um, but in this direction, but it's unbraced in the strong direction. The strong direction is this way, bending this way, bending uh, this. Actually, the way I'm drawing it is probably awful. The proper way of drawing it probably is drawing the axis of bending, and then probably something like this. Uh, yeah, and that showcased that this must be like that. Anyway, this is uncontrolled here. Therefore, it can bend like this, is what's saying. And it's free. So K equal 2 for this one. Well, this one is still K equals 0.7. We know what this is. This is 6.1 megapascals from question number 7. So we don't have to even look at this anymore. We have to look at this one and see what we get. You might be saying, golly, what a complicated way of looking at it. Yeah, that's why you grab a book to make it understandable. Now, I'm going to bring out my video to showcase this again. This time, we're going to use a hollow cube instead. So I'm just going to showcase this a little bit because I think it's pretty interesting what this thing is doing. Let me just grab this piece of paper and mold it into like a hollow out version of itself like this. Okay. So over here we have a hollow. It kind of looks like that. So if I was to fix this in place, this over here is the weak direction. This direction, where it's going like this, is the hard direction. So you can imagine what it means. I wish there was foam. The foam would be much appreciated. But the weak direction we already calculated. We need to calculate the hard direction, which is moving this and this way. So you can imagine by making this 3D thing, how to brace it. The bracing to stop the strong direction would be on the side. So it would, I'm drawing it wrong over here. It should be on the side. The stop braces should be over here, and stopping the braces over here, which is clamping on like this. And then we should be good. So I wish you had foam. My recommendation is for this project, if you were to like teach it to a class, is get a foam cutter and get a rectangle foam and cut it. And that would be wonderful to explain to a class, I think, because I'm realizing this paper is too flimsy. Maybe this is better, this book. But yeah, this book is better, but the spine over here makes it kind of hard to like explain. I'm trying to look for a different thing, but I just couldn't find. Oh, wait, I have foam over there. Give me 5 seconds to go there real quick. Ah, here it is. Boom. So imagine turning this way. This way is easy, but turning it this way, that is way harder. And if I was teaching a class, probably say pass this around a little bit. But you can see this much. There's plastic in the middle, but that plastic is orientated the same way, so it would apply the same way. So you can see it's much harder. Well, that's the visualization, 3 cents of visualizations. Okay, so we know already from previously that 6.1 meganewtons for the weak direction. So I should probably read this. A steel column with cross-section of 12 by 16 is 4 meters in height and fixed to the base. The column is braced against the buckling in the weak direction only by pin connection on the top, but is unbraced in the strong direction. So the strong direction, and the modulus SSA is 2.1 times 10 to the megapascals. What is the maximum theoretical vertical load that the column can support without buckling? So here again, we're gonna go over here and apply this equation over here, which is the play equation, not play, the critical equation. And I will say this critical equation is very powerful for you to like know, in my opinion. You have to know it a little bit. So for the other direction, it's actually 2 multiplied by 4, and it's going to be parentheses squared by pi e, and then square. Sorry, don't forget the square also, PCR, and then I, and then the I over here is different. And all of this has to change a little bit. The E has to change to 2.1 times 10 to the 5, and then again I said times 10 to the 6, right? That is definitely absolutely needed. And you have that. And next thing is the 12 divided by, no, not 12. Now, the strong direction is 16 by 12 to the cube. We will change that. And then 1 divided by 100, I believe, to the fourth power. And then this thing is 2. So you grab your calculator. You have your previous equation, which has indications of already having all the numbers in there for you already. Just switch up the 16 and 12, and then change it to 2. You get this PCR to equal 1.32 megapascals. So that is A right there. I get 3.1.326474.831, and if you're wondering. And if you want, you can keep your newtons in mega, so it gives you mega automatically, but it is A. The solution is A. One way or another, it gets you A. Okay, next question. We're almost done. One more for this section. A 10 by 10 cube, a square column supports a compressive force of 9,000. The load is applied to the eccentricity. So eccentricity, it says in the neutral axis 2.5, this load is applied, and that creates a moment. Along the axis of symmetry, yeah. What's the maximum tensile stress of the column? So this is P over A plus the my equation. Thank you, Dr. Chi again. I love Dr. Chi because Dr. Chi taught me this, and I was like, woohoo, that was easy. Because I mean, how would you memorize that? And I was thinking, yeah, memorization is hard. But then she just said, oh, just remember the my equation. Be selfish, my. And it says MCI. And that's a selfish equation. Selfish equation. And that's how I memorized it from now on. Anyways, compressive force 9,000. Multiplied by 2.5 divided by 100. That's equal to the moment. So 900 newtons multiplied by 2.5 divided by 100 is that. So 900. Oh, wait. The load is applied to the centricity. Yes, and then YC is basically going to be the top. You'll see what I mean. Divided by 100, and it's going to be multiplied by 5, I believe. Divided by 100. Okay, that's C. And then selfish equation, the really selfish, big bastardized equation. Like think of the most selfish human being on Earth, and that is how I remember it. So it's 2.5 divided by 12, right? Into the fourth power for this one. And over here, you need, because of that fourth power, 100 by a 4. Now, I would recommend, again, doing it one at a time. So do this one first in your calculator so you don't break your calculator. So I'll do 900, 10 multiplied by 10, multiplied by division, 1 over 100 square. So that gives me 900, 3 more zeros. Over here, I'll schedule the other one. 9,000 multiplied by division, 2.5 divided by 100, multiplied by division, 5 multiplied by 100, and then the bottom. There probably was an easier way to do it, but here's the thing: the units actually matter for cases with addition. When I said that the units don't matter, it only matters if every operation is multiplication is ABCD, because it doesn't matter if you have a question that's a little bit off by a scale of something. But here it does, just so you know. Okay, so do be careful about that. Yeah. Anyways, I should probably make sure that everything is correct. Uh, wait, this is supposed to be 5. Why is it 2.5? Don't know why. How? I was looking at that and saying that doesn't look right. Del. Okay. All right. That looks proper now. All right. And 4 divided by 12. Okay, I get. Interesting. I don't seem to. Oh wait, this is supposed to be 10. My apologies. I think I was it's not getting any of the answers because I put 5 instead of 10 for that one. So let me just change that back. All right, so now I'm getting something. 135,0,0,0,0. That's the top. I get never thought of that, but so here's the thing. This is asking, I made a mistake over here earlier. This is asking for tangential, not compressive. So it must not be negative. And this time it matters if it's negative or positive because the directions are different. So it's important to know that this one is negative because it's pushing inwards to the blocks over here. If you look at this compressive, so it's negative. So we can do 900, and then we can do minus plus 135,0. This gives us 450, and that is the one that is going to give us the tensile force. It's showing that at over here, um, or is it over here? There is a tensile force because it's basically showing us um something. Well, the other force is 1, 2, 2, 5, 0. So it's actually something like this, where it is like that. Look at this. Yeah, that probably is over here, and that's how it shows up. So it's A. Now, here's the thing about the next question. I already did this. All right, the next question is kind of bullshit. So I don't like this question. Is a square column with a solid cross-section area is placed in a building to support a load of 5 megapascal newtons. The maximum allowable stress in the column is 350 megapascals, and the column reacts linearly to all loads. If the contractor is permitted to the load, the column anywhere in the is 1/5 the cross section. What is the smallest possible dimension of the column? So here's the thing about this one. It's kind of bullshit because you can do it. I don't mind you. This is the max output because of the line of symmetry over here. Um, so here's the thing about this one. This is one that requires us to do some fancy stuff. It's going to be using my equation 2 times, one for the x kind of like force and one on the y kind of force. And yeah, we can do this. We can do all of this and figure out the c, whatever the d is. I think I'm just going to leave this one because this one is actually a pain in the ass to do, in my opinion. I mean, it's not really that much of a pain in the ass to tell you the truth. I can do it. It's just that I don't think it's actually worth it to tell you to learn about this one. Sure, I mean, we can do this. This is basically 0 0.2, right? Over here is 0 0.4 and 0 0.4. And then B is not given, so they must be basing over here. And then you can do like force times E over here. E is about like 0 0.1 B. So you can do like F, which is already given, A, plus or minus. And then we can do um this whole entire equation. F multiplied by um 0 0.1 B, parentheses, and then whatever b divided by 2 is because you need this thing, and then divided by the moment inertia, so it's like b to the 4 to the 12. In my opinion, this equation is not worth it to learn, but if you want to learn it, here you go. Um, yeah. So you can keep on going and do this whole thing because the most stressed corner is these corners over here. So you're just gonna do those corners and then just gonna figure it out. In my opinion, you can do it. It's not really that hard. But I don't feel like it's a real question every exam. There's no way they'll give you this thing.